in this lab, our target is to calculate the experimental value and the expected value of the centripetal force of an object. This lab will be dealing with a circular motion. So the motion of the object will be a circle path. We need a rotating platform. We need to make sure that the platform is perfectly horizontal. A center post at the middle of the ruler, so at 0 centimeters, with a spring, a side post to hang our object, and a pulley. So the spring is hung on the center post, and it will be connected to our object. Then we need to add a hanging mass to obtain the equilibrium. So applying Newton's first law, okay, we can find the tension on each branch. Okay, here we have a spring, we have a hanging mass, we have the weight. So we need to add the required mass needed to obtain the equilibrium. How do we know that we are at the equilibrium state? The vertical string here, the one that we are hanging the object on, should be vertical. So it should be parallel to the black line. So we can move the central post, or we can add extra weight. So we need to add weights. Let's try with 50 grams. Don't forget here that the hanging mass has a mass of 5 grams. So here we have 50 grams. Okay, the object is shifted. Now we need to move the side post to obtain a perfect vertical line. Okay, so we are at 17 centimeter. So the distance between the center post and the side post is 17 centimeters. So the radius of our path is 17 centimeters. The expected value of the centripetal force is equal to the weight. Applying Newton's first law, we can calculate Fc. Now we remove the hanging mass. So we have lost our equilibrium. We need to apply a rotational force to obtain the equilibrium again. Okay, before removing the hanging mass, we need to know the position of or where was our equilibrium. So here we have the pink indicator and the black hole. So the black indicator and the pink indicator have the same level. So if we remove the hanging mass, the black indicator has moved up and we have lost our equilibrium. So our target is to apply a force and to get again the pink indicator into the black hole. So when the pink indicator is in the black hole, we are at the equilibrium phase again. And we can calculate, or we can obtain the time required to find, for example, 10 rotations. So in this part, the mass of the object will be constant, the hanging mass will be constant, so the centripetal force is constant. All we have to change is the radius and to measure the time required to complete 10 rotations as a function of the radius. After finding the time required of 10 rotations, we can calculate the period. The period is defined by the time required to complete one rotation. so one circle. So we will count 10 rotations, find the time of 10 rotations, calculate t, and then we need to plot r versus t squared. After plotting r versus t squared, you can calculate the slope. And after calculating the slope, you can calculate FC, the experimental value of the centripetal force, and you will compare the two values. The expected one was the one calculated from the hanging mass, so it was the one calculated at the equilibrium phase, while the experimental one is the one calculated from R and T, from the slope. And here we need to make sure that while rotating our platform, okay, we need to make sure that we are applying, or we have a constant speed. So how do we know that we have a constant speed? The pink indicator should be at a constant level, okay, should not deviate, deviates up and down. Okay, so I need to make sure that I'm applying a constant speed. After applying a constant speed, I can start counting 10 rotations. And while I'm counting 10 rotations, we'll need a stopwatch. Okay, this stopwatch will be used to measure the time required for these 10 rotations. Okay, so I will start by trying to obtain a constant speed. Okay, so now start 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Stop. So the time required to complete 10 rotations for a radius of 17 centimeters is now again we will change the position, the radius. We were at 17 centimeters. Let's try 16 centimeters. So to know the exact position, we need to check the black line and the graduations or the divisions of the ruler. So the black line is exactly at 16 centimeters. Okay, don't forget that we have error on the radius, which is the smallest subdivision divided by 2, while the error on the time is, it's a digital stopwatch, so it's the smallest digit. So again, we need to apply a force, okay, a rotational force, and when we obtain a constant speed, now we start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 rotations. So now for 16 centimeters, it's 14.44. Okay, we need to take 3 significant figures. So it's 14.4. The period, it's 1.44 seconds, and then we will square t. We'll repeat the same procedure for 2 more radius, 15 centimeters and 14 centimeters. Okay, you will plot r versus t squared. Okay, if we're plotting r versus t squared using linear regression, you will find the slope. Okay, what's the relationship between r and t squared? As we know that v is equals to d over t, and d in our case it's 2 pi r times n. N is the number of rotation. T is equals to t, the period, the time required to complete one rotation, times n, the number of rotations. So v, it's 2 pi r over the period t, And as we know, using Newton's second law, Fc, it's sigma F, it's ma, and AC, it's V squared over R. Okay? So Fc is equal to M AC, it's equals M times V squared over R. And we have the relationship between V, R, and T. We can obtain the relationship between V, T, and Fc. So we replace V by 2P over R, M Fc equals M V squared 2 pi R over T squared over R. So Fc, it's M 4 pi squared R squared over T squared R. Fc, it's M 4 pi squared R over T squared. So R is equals to T squared Fc over M 4 pi squared. This is your slope. You have the value of M, which is 200 grams. You need to convert it to kilograms. 4 and pi squared, you know the values. You can calculate Fc in newtons. This will be your experimental value of Fc, while the expected value of Fc will be calculating using the fact that Fc is equal to the weight equals mg, and in our case m was 55 grams. Okay, and you compare the two values of Fc.